she's going to be the forward reaction. He's going to be the reverse reaction. Okay? And so initially, what you'll do is you will take and just dip and then pour. That's the forward reaction. Okay? So at the very beginning, it's all forward reaction. So you dip and pour back.
Dip in here?
Mm-hmm. You can't scoop. You just have to lay it down and pick it up. Okay? Pick it up and pour. So see, reverse reaction's almost nothing. So now you dip and pour. Just like that. And now you dip and pour. I want you just to keep doing that. Do it one, then the other, one, then the other. Do you notice that the reverse reaction's a little bit down?
Yeah.
Forward reaction's very big, going forward. Reverse reaction's getting a little bit higher. Forward reaction's still greater. We'll do this 7 or 8 times, so just keep going.
I'm not gonna drain all of it.
What's going to happen eventually?
It's
even. And that is what?
Oh, equal.
That's what equilibrium. Okay? So eventually, we're going to reach the point where the forward reaction and the reverse reaction are exactly the same. That will mean that there's going to be no net change in the volume. I put blue food coloring in the water so that you could actually see it. But that's what happens in a reversible reaction. There is this ability to reach an equilibrium constant. Okay? So what do you think? Are they about even?
About, yeah.
Yeah, pretty close. Okay? Pretty close to being even. Forward and reverse reaction are equal. So now, to show you what can be a very small K, we're going to start back. And you get to use this. And you get that.
Cool.
Okay? All right, so in this, we're starting this reaction, but here the beakers are not the same. So the forward and reverse reactions, it's not going to go until they're even. It's not going to go to the point that they're even. Still not. Okay? You'll still get to a point that the forward and reverse reaction are equal, but are they going to be at the same level? No. Then you're going to see that there's going to be a difference in terms of how much is moved in the forward and reverse. See, he's finally got little. But you see that her forward reaction is kind of the limit because she's got the little beaker. That's what you see when you have a K value that's really small. There's not a lot of forward reaction. Most of the reaction is in reverse. So there's going to be a lot of reactant and only a little bit of product that ends up being formed comparatively. And if they switch speakers, what would happen?
Then there'll be more over here.
Then you would end up with a whole lot more product. That would be a K value that was really big. So it's really the forward and the reverse rate sets up an equilibrium, but they don't necessarily have to be exactly the same.
With this one.
That's what the K tells you. If they are exactly the same, then K is 1 because the amount of product and the amount of reactant would be equal. But if K is a small number, that means there's a lot of reactant, not very much product, which is what we're doing right here.
So what, won't these eventually kind of?
Eventually, the volumes will be the same, but will the levels be the same?
No.
No. Because your big beaker can pick up this, it's got like wider base, it can pick up this volume, but her beaker, she's kind of like maxing it out each time. She can't move more than that 50 ml beaker. So you dip yours and see how much is in there. Oh, that's all right. Do one more.
Oh, yeah.
Do one more. So we're doing a reverse. We should be about at equilibrium. So you dip yours. How much do you think's in there?
Yeah, 80.
Maybe about 80. And now you dip yours.
About 50.
Okay, so still not 100% there, but you do notice that there's very much a difference between. That there is more reactant, less product. So that's what K tells you. So this tells you the relative amount of reactant and product that you have when you're at equilibrium like this. Okay, thank you. Thank you for the.
Good job.
Which acts as the acid, which acts as the base. And then on the product side, you can identify which would be the acid in the reverse reaction. That's the conjugate acid. Which would be the base in the reverse reaction. That's the conjugate base. So remember I told you the last one, I said, so the trick is whatever acts as an acid in the forward reaction is the conjugate base of the reverse reaction. Because whatever loses its hydrogen is going to gain the hydrogen in the reverse. So if you look at B, this bottom one, you tell me which one is the acid. Is CO3 2 minus or H2O? Because, okay, so if we go, in each case, always just look at the reactant and find the pair on the product side that looks the most like it, and then compare to determine what happens to the hydrogens. And it really is the hydrogen ion, but if you just follow the H, that's really, so you see that this goes from H2O to OH minus, so it loses H plus. And by definition, donating a proton, donating a hydrogen, or losing a hydrogen, that is always a acid. But that means that OH, the hydroxide group on the product side, if you look at it in reverse, going from OH back to water, that would be gaining the hydrogen back in the reverse, and that's why they call this the conjugate base. So whatever is the acid on the reactant side, its pair will be the conjugate base on the opposite side. Same thing here. Take CO3 2 minus, compare it to HCO3 minus. What happens? So that acts as a proton acceptor or a hydrogen acceptor. It gains the hydrogen, however you want to think about it. That is the characteristic of the base. So then on the product side, that HCO3 minus, in the reverse reaction, that's going to lose that hydrogen to convert back to CO3 2 minus. So this is going to be the conjugate acid. So you see this in weak acids and bases. They set up equilibrium so that if you add water or if you add CO3 2 minus to this, that will cause changes in the equilibrium and will cause shifting of the balance of them. And it really just depends on what their ratios exist as to begin with. But remember in Le Chatelier's principle, so if I have this one up above and I add, so if first it's at equilibrium. So that means in the beaker, I have all four of these things. I have H3PO4, I have NH3, I have NH4 plus, and I have H2PO4. Because if it's at equilibrium, you got them all. Okay? So it's at equilibrium. What is going to happen if I add NH3? That's going to affect the equilibrium. It's going to disturb the equilibrium. And in order for it to re-establish equilibrium, which way will the reaction shift? Forward or reverse? What was the rule? So we can actually think back to this. What if, so if I'm adding NH3, it's really like I'm adding this. So it's as if I go, okay? So what's that going to do? It was at equilibrium. Now I just dumped a whole lot of reactant in. And so if I go ahead and start, what's this going to do? What will happen to my forward reaction? Will I have the same amount or am I going to have more? More. So that means the forward reaction will increase. The reverse reaction, about the same, right? But the forward reaction is going to be greater than it was until you reestablish the balance again. So if I add reactant, the forward reaction will become greater to try and rebalance it. What if I take, and I just take some out. So if I take out product, okay? So if I take out product now, can you tell that it's all back up? So you can tell that it's out of balance. So which reaction will be greater? Okay, because it's, see how much more is in there? So I can put more in this beaker because the level's higher. So if I remove product or if I add reactant, the forward reaction will increase. Exact opposite happens if I do, like in this one then. So if I add NH3, which way will the reaction shift? Forward. To restore the equilibrium, I'm going to increase the forward reaction until I restore equilibrium. And so I told you, you can think of it as being like the seesaw. So in this one, if I add NH3, it's really like I just add in more product. Sorry, I add in more reactant, so it makes that side heavier. The only way to try and bring it back is to take some of the reactant and convert it to product, to bring the balance between the two back. So this happens until they're back at equilibrium. What if I remove H3PO4? Then I'd have to have the reverse reaction to try and put some back. Okay? If you take away from a system that's at equilibrium, the reaction always shifts towards whatever you took away. And if you add anything to a system that's at this perfect balance, if you add, the reaction always shifts away from whatever you add. So if I remove H3PO4, that's going to make my reactant side less compared to product. And so the only way to bring it back is to have the reverse reaction occur until I get back into the balance. So in this one, it'd be the reverse. If I add a substance that's at equilibrium, the reaction always shifts away from whatever I added. And if I remove a substance, it doesn't matter if I remove product or if I remove reactant. If I remove a substance, the reaction will always shift towards whatever I add. It will shift towards whatever I removed. Okay, so we'll do a couple more of those next time, but we went on with this, looking at this equilibrium balance and talking about the fact that water actually forms ions. The problem is that water, its K, which is product over reactant, its K value, here's the product, the K being H3O and OH, and then the reactant being just water over on that side, it's so small. It's 1 × 10 to the minus 14. So it's a very, very small amount of ions that are formed, but it is a known dissociation constant or equilibrium constant that water has. So they said, okay, well, if water has equal amounts of acid or base, then that means that I have 1 × 10 to the minus 7th molar acid and 1 × 10 to the minus 7th molar base in water that forms ions, which is how I get the 1 × 10 to the minus 14th, because exponents get added together when you multiply them. So they said if hydrogen and hydroxide are equal, we can use a logarithmic value, which is the pH scale. So we really took the exponent. So this exponent value, if you use the log of it, it takes the 1 × 10 takes that part out, and it really just puts the exponent as that value. So that's how they came up with the pH scale and having a pH of 7. So a pH of 7 is the fact that water has 1 times 10 to the minus 7th acid concentration, or hydrogen ion concentration. So in this, looking at some of the normal ones, remember we went through like the strong bases versus the strong acids. We looked at the ones that are considered mild acids. These ones up here, these are really mild bases. Those are the things you come in contact the most with, and they have the least amount of ions, the least amount of damaging corrosive ions. But when you get above 11, 10 and 11, when you get down below 2, those are when you have lots of ions, and those are the reactive hydrogen ions or hydroxide ions. So I gave you just sort of examples of them. Calculating pH is actually pretty simple. It's just a matter of remembering how to put the information in your calculator straight. So I brought calculators. So if you need a calculator, I have 4. Anybody need a calculator? You need a calculator that can do logarithmic, okay? So you have to be able to do logs on it. Those 2. You guys share. Oh, you got one? Good. Okay. So I want you to just practice so that you make sure that you can. When given an acid concentration, if it's a strong acid, like hydrochloric acid is a strong acid. So if we have a 0.05 molar hydrochloric acid solution, this is a strong acid. That means as soon as you put this in water, it makes 100% hydrogen ions. So the concentration equals the hydrogen ion concentration. So H plus equals the molar concentration. So if it's 0.050 molar, you can use this directly in the pH calculation. So how you do this, if you have a graphing calculator, you put it in directly. So if you have a graphing calculator, you want to put negative and then log and then 0.050 and then equals. Okay, so if you have a graphing calculator, not like mine, you hit minus and then hit the log button. Like the minus means like the plus minus button. Hit the plus minus button, the log button, and then put in 0.05 and then equals. Okay, not if you have that. That's if you have the graphing calculator. So if you have the one that the big $120 one, that's how you put it in. If you have the old school, that's mine. You put in the concentration first. So you put in 0.050, then you hit log, and then you make your answer negative. So you do it in reverse. Okay? So put in 0.050, then hit the LOG button, and then hit the plus minus button. Did you get 1.3? Mm-hmm. Okay. Try it again. 0.050, log, plus minus. Yes?
I'm sorry,
Uh-huh. Do you have a plus? Uh-huh. That's the plus minus button. The plus minus should be at the very bottom. Yeah. So it's just to change the sign. Okay? Because it always comes up with, because this would be 5.0 times 10 to the minus 2. And so it takes the minus 2 and it takes away the minus part. Because when you take the log, you're really getting that exponent value is coming into play. Okay? So that's how you get that. Okay? So depending on which calculator type, and you figured out which ones of yours.
I use the graphing
you use.
calculator.
Okay, so you go based on graphing calculator.
I tried it that way and it goes error.
Uh-huh. Yeah, and it depends because yours looks like a normal one, but it actually I think it's easier if you just put it in straight. You just hit minus log and the number and hit equals, and it gives you the right answer. So it just depends. The old school calculators don't work that way. Any acid, okay? If I give you the concentration of any strong acid, you can figure out the pH. As long as it's in a molar concentration, that's moles per liter, you can figure out what the pH is. If you know the pH, you can work backwards and figure out the concentration of the acid. So in this one, it's really doing the reverse. So if you have a graphing calculator, you will put the inverse log of the negative pH. So the inverse log is second log. So you hit the second, you hit the second button, then you hit the log button, and then you'll get the parentheses, and you just put a negative of whatever the pH. Hit the plus minus and the negative and the pH in there. So try this one. So this one says the pH of a solution is 3.00.
I did second log and 10 comes up.
So you did second log negative 3.
It's showing me 1/1,000. So.
Okay, yeah, which is what that is, okay? And so that's the graphing calculator. If you have the old school, you put in the negative pH. So you would put in -3, and then you hit second log. And you should get 0.001. You might get 1 times 10 to the -3.
Yeah, that's what I got.
This one should be 3 negative, second log.
Oh, I did put the negative. I put regular 3.
Oh yeah, you have to put 3 and make it negative. So you have to put the negative pH and use your plus minus button to do that. Okay? So put the 3 and make it negative, and then hit the second button and the log button. Did you get that?
Yeah.
Yes? And you got 0.001? Or you might see 1 and then up here -3. Or doesn't it look like -0.03? If it puts it in scientific notation. If it puts it in scientific notation, remember you get those 2 little numbers that are smaller in the far right end?
Yeah, just keep it.
What does it look like?
Whatever.
Oh, yours says 1/1,000. Well, that's pretty fancy. Well, and it says 10 to the -3.
Yeah.
Yeah, so that's 1 times 10 to the -3. So it might say that too. So those ones, it's just a matter of like looking at them. So we'll do a couple of them. So what is the pH? And all of these, I'll only give you strong acids. Because weak acids, you have to take the K value and then work out and figure out what the pH is. We're not going all that, okay? We're just going to do the strong acids because the concentration is the acid concentration. So what is the pH of a 2.5 times 10 to the -6 molar HNO3 nitric acid concentration? Try that one. See if you can get that one set up. What'd you get? 5. So you have 2 significant figures because 2.5 times 10 to the -6, you want to make sure you keep 2 significant figures. So you got what? 5.6? I gave out all my calculators, so I don't know. So did you get that?
I have a negative number.
we're gonna make it negative. So you make minus log 2.5 EE minus 6. Right, so remember you can use the EE button, and that's another challenge too. 2.5. 2.5. Then, so in this one, 2.5 EE minus 6. And then hit log. So 5.6, and you'll make that positive. So it comes out a negative number. 5.6. From that one, so remember see that EE, that means times 10 to the, okay? So you want to put in 2.5, and then you have to go second EE, okay? And then 6. And then 6, and make it negative. And then hit log. Oh no, so yours you gotta do it straight. So yours, you will hit minus log, and there's your part. So then you're gonna hit 2.5 EE negative 6. Okay, so you put yours in straight. Put it in straight. Don't do the old school. Do it like you would a graphing calculator.
I don't have
So it really just depends.
I don't have EE. I did second and then E in the end.
We saw EE on this one. EE is times 10 to the. See that? That's it. So
Okay.
and so it puts in times 10 to the, and then you just put your exponent in. Did everybody figure it? Did you get 5.6? Yes?
Oh man.
Chelsea? Is that okay? Oh, slide over and look
She can
to
have this
see.
one. I have one in my bag.
You have another one? Yeah, because this is the reason people miss these questions. It's not that it's hard, it's just that they don't know how to put it in the calculator. And so trying to put it in, so in this one, you put in the concentration first. 2.5. And then now put in minus 6. Now do a log. Now, this is the old school calculator. The old school calculator, you put in the concentration, then you hit log and you make your answer positive. Like that's like the only calculator that I had when I was in school. That's just how you do them. The new graphing calculators, you can put it straight in. You put minus, you put in log, you put in your concentration and hit equals. It goes straight. So the second one, we're working in reverse. So the second one, you know the pH and you want to know what the hydrogen ion concentration is. So instead of going in this direct way, you end up going, you want to find H+, and that is going to equal the inverse log of the negative pH. New calculator, or like new graphing calculator, just put it in straight that way. Just do second log and then negative of whatever the pH, and you should get your answer. If you have an old school calculator, you put in the pH. So put in 3.80, make it negative, then hit the inverse log, hit second log.
Yeah, really big number.
But we're only going to keep 3 significant figures. So what's the number we got?
0.00015.
Right? Did everybody get this? If you have it in scientific notation, it might have said this. Do you see that those are the same? 4 decimal places to make it in scientific notation. So you might see it in either one of these ways, but I only need 3 significant figures. So which ones are, what do I keep?
0.00015.
And then what happens to the rest?
It drops off.
It drops off.
If we had this question on a test,
The final's gonna be multiple choice, right?
There's another test. There's a fifth exam.
Right, but would you have both of those answers up there? We have to choose one, like as a multiple choice, or?
No, I wouldn't have both of them up
well,
there.
obviously-
I would have one. I would have one or the other. But you should be able to look at those two numbers and see that they're the
Okay.
same. Okay, to go from scientific notation to like expanded form is what they call the ones with all the zeros. But that's why I wanted to show you that those are both the same. And you can actually figure that out on your calculator how to switch it. You can switch from scientific notation to expanded form as long as you don't have a Casio. Don't ask me to how to figure that one out. I can't do it on those. They're crazy. All right, so well, here's the last one. If an HCl solution has a pH of 6.34, what is its concentration? Is this one like the top one or the middle one?
The middle.
It's just like the middle one. Plug it in the same way, just like the middle one. Did you get it? Not yet. So you see that these two are both the same. Okay? It's just that the bottom one is written in scientific notation. But I would still round to 3 significant figures. That would be that answer. So what did you get?
6 zeros, then 4, 5, 7.
4, 5, 7.
Keep them all.
Concentration, capital M, molar.
So the middle one would be molar also.
Yep, capital M for both of those. pH doesn't have a unit. pH is just a pH, it's just a number. It's just 5.6 is its pH. This one, you might see 4.57 times 10 to the 7. Did you get that? Sweet. So it's not that bad. It's just a matter of being like, go back over with your calculator that you'll use so that you're like, okay, do these steps. So that you've got that part straight. So those two, so on yours, you're going to go straight through. So hit second log negative 3.8 and then equals. Did you get 0.000158?
Yeah.
Okay, yeah. You have to put the negative in front of that pH in order to put the exponent in correctly for it to switch it back to the exponent type. Okay, so we'll practice a couple more of those again. Last topic in this chapter, it's not math, it's just a theory thing, and it's all about what's called buffers. So pH in your body, very strictly controlled. You don't want pHs to change dramatically because that means you would have more hydrogen ion or more hydroxide ion, and that would end up affecting how proteins function. It would end up affecting things like the shape of enzymes. We did that in lab. In lab, you took the lactose and you added acid or you added base, and then you added the enzyme to it. People that added acid, nothing happened. Like theirs, it was like non-functional the entire time. That is because excess acid or base ends up having an effect on normal cell function. So a buffer, by definition, it's a pair of molecules. It is always a weak acid and its conjugate base, or a weak base and its conjugate acid. So the weak acid in this one is H2CO3, carbonic acid. Carbonic acid is a weak acid. It doesn't dissociate very much, but it's still an acid. Its conjugate base is the bicarbonate. So it can exist as sodium bicarbonate or just as the NaHCO3, but it's this acid and its conjugate base. In fact, you make this in your blood just by carrying carbon dioxide. So carbon dioxide made by your cells goes into the blood. It dissolves in water, which makes carbonic acid, and a small amount of that carbonic acid dissociates and forms the bicarbonate ion. So in your blood, just because of breathing, you have the buffer pair. So you have a weak acid and its conjugate base. So that's a weak acid and a weak base. Weak acids and weak bases don't make lots of hydrogen ions. They don't make lots of hydroxide ions, but they're really good at neutralizing, right? That's why you take antacids when you have indigestion. They'll neutralize acid or base, but they're not going to create a lot of ions on their own. So here's what happens. If you have the buffer pair, so here's the pair, carbonic acid and bicarbonate, you have the weak acid and its conjugate base. If a strong acid gets added into the blood, the base part of the pair will neutralize it. So the bicarbonate will react with hydrochloric acid, because remember that hydrochloric acid, if it hangs around, it'll make lots of hydrogen ions. Lots of hydrogen ions will end up affecting normal function. Corrosive, reactive, damaging to tissues. So if hydrochloric acid gets dumped into the blood, the bicarbonate, the base part of the pair, neutralizes it. And it converts it to what? A weak acid. So it takes a strong acid and converts it to a weak acid. And so in doing that, the pH doesn't change. So that's going to create, it's almost like it mops up any acid or base that gets added. It helps to neutralize added acid or base so that you keep the pH the same. So these two pairs are like sitting in fluid. And so acid comes in, one pair reacts. Base comes in, the other pair reacts. And as long as it happens sort of in a moderate amount, you will never have a change in pH. 99.9% of people, their blood pH stays between 7.35 and 7.45. That is the pH of the blood. And for 99.9% of people, that's where it stays. And it stays because of this acid-base buffer pair. The second one I have here again, here's the base, here's the buffer, carbonic acid and the bicarbonate ion, the weak acid and its conjugate base, they're both sitting in the blood. And then, this wouldn't happen, but let's just say some sodium hydroxide got dumped into your blood, just like Drano. That would be bad, okay? Because that strong base is going to make lots of hydroxide ions that would be very reactive. Strong bases that would be damaging, but which buffer pair can react with that? If we have a strong base, what do we neutralize it with? The acid. So then here, the acid will react with it and it'll convert it to a weak base. So it'll take a strong base that makes a lot of ions and convert it to a weak base with fewer ions. And then the pH doesn't change. Yep, so you have this buffer pair, and the buffer pair really is an acid and a base together. You have the weak acid and its conjugate base, so you have an acid and a base. If any base gets added, the acid reacts. Any acid gets added, the base reacts. And the goal is we're going to convert strong acids and bases to weak acids and bases because those don't make a lot of hydrogen ions. Those don't make very much hydroxide ions. Those are not going to change the pH, and it's going to help us to keep this blood pH constant all the time. So you actually have buffers present in every single fluid. So the cellular fluid has buffers, the blood has buffers, all of your secretions and everything, there's buffers in them, and the buffer just does that. It just converts any strong acid or base to a weak acid or base, and that's going to prevent any change in pH. What happens though if you have an imbalance where your body is making a lot of acid, where it's making more acid than the buffer can handle? If the buffer gets overwhelmed, which is sort of like you've got the little acid and base, and so if acid keeps getting added and added and added, eventually you're going to run out of conjugate base. Eventually you'll run out of base to neutralize the acid, and in that case, the pH of the blood begins to drop. That is termed acidosis. Acidosis is when there's so much acid in the blood, the buffers can't balance it out, and the pH goes below 7.35. So I said 7.35, 7.45, that's the narrow range. Your blood is slightly basic. But look at what does acidosis. Causes your nervous system to start shutting down. Like it has that dramatic effect. The person is really tired, lethargic. They may seem very disoriented. They'll have a depressed heart rate, lowered blood pressure, less alertness. In fact, they can go into a coma. If the blood pH drops below about 7.1, that can be fatal. That can actually suppress heart rate altogether and respirations. Person stops breathing and they don't survive. So too much acid can end up having a fatal consequence. Alkalosis is the opposite side. So you got your acid and your base in the blood. If any acid gets added, the base reacts. But if any base gets added, the acid reacts. This doesn't happen as a big, huge, that doesn't, usually you end up with too much acid, but this can happen on occasion. But if you have too much base and the buffer gets overwhelmed, then you call that alkalosis. So alkalosis is too much base, acidosis is too much acid. Alkalosis has the exact opposite effect that acidosis has. So acidosis, everything starts shutting down. Everything gets like hyperstimulated. So you'll notice a person's heart rate will be up, their respiratory rate will be up. Oftentimes they seem like shaky, really nervous acting. Problem is they can have convulsions. So rather than like losing consciousness, they end up having a convulsion, in uncontrollable muscle contraction. They can end up developing a heart arrhythmia. So their heart's like beating so irregularly that then it starts to fibrillate. So they can end up having a heart attack and dying. So extreme, both can be fatal. So extreme cases, and I told you 99.9% of people never have this issue because of buffers. Buffers are there, and most of the time you make a little acid or you might have a little base present, but you rarely have extreme amounts. But those are still issues that you may be dealing with patients especially that have some chronic disease. Maybe their liver's not working properly, maybe their kidneys not getting rid of acid. So if their kidneys aren't functioning properly, then you can end up with acid-base imbalance. Maybe they have a metabolic disorder and they're either making too much acid or making too much base. And so you're trying to balance those fluids and keep that pH in that normal range. So it depends on which one. So like with acidosis, they'll start giving them bicarb. Okay? So too much acid, they'll give you bicarb because that's the base. So they'll actually give you bicarb, which is a blood buffer pair. It's the conjugate base of carbonic acid, but they'll give you that to try and bolster that balancing of acid. Oh, look, there's another concentration. There. But most of the time it's because of one of two reasons. It's either a metabolic cause or it's a respiratory cause. So we can have metabolic acidosis. Metabolic acidosis is when the body is making too much acid or it has lost too much base. Example, untreated diabetes. Because if you're not taking insulin, what happens to your blood sugar? Stays really high. You have all those issues of the hyperglycemia, but your body cells say, we're starving. The body cells don't know there's sugar because there's no insulin. So if there's no carbohydrate, the body cells start to burn fat. And the byproduct are keto acids. Because you can't utilize carbohydrates, because of no insulin, fat metabolism produces keto acids. So you have the person like they're waist away, you start noticing they have muscle mass loss, all these other factors, but the keto acids is what ends up affecting the pH. That can put them in metabolic acidosis. For this, the important thing is treatment. Okay? You need to be able to treat the disease to stop the acid production. And in fact, with most metabolic disorders, that's a necessity. You've got to be able to do that. Respiratory acidosis, though, remember I said you make your blood buffers because of breathing. So you carbon dioxide in water makes carbonic acid. And then carbonic acid generates some bicarb. So just breathing creates the buffer pair. So if somebody's respiratory system is damaged, then they can't get rid of carbon dioxide. So what's an example of where your respiratory tract is damaged, where you have lung damage? Emphysema, COPD. Okay, so what do you notice with the patient that has emphysema? What do? They struggle to breathe. Okay, they may be blue or they might even be kind of pink at times, depending on it. But this is because of lung damage. So remember we were talking how diffusion occurs, oxygen diffuses into the blood, but it has to diffuse across that membrane from the alveoli, the air sacs in the lungs, into the blood. And if you have a lot of scarring, then there's not a nice thin layer. You end up with a really thick layer and the gases cannot diffuse well. So you can't exchange oxygen and carbon dioxide. So one problem they have is that their oxygen levels are low. If their oxygen levels are low, how do they feel? Really weak, okay? Because oxygen is used by your muscles to power movement. And so for them, very, very slow. They're not able to move at a very fast pace, and that's because they can't get oxygen into the blood because of damage to the lungs. So that's one, like symptoms that you'll see is they're going to be super tired. They get winded really easily. My grandfather died of emphysema, and like eating tired him out because you don't realize it, but when you're eating and chewing and swallowing, you stop breathing, right? So you're like, and then you like resume breathing. Normally, if your lungs are fine, then that's not an issue. But for him, just eating would mean that he would be actually like struggling to breathe a little less, and he would get winded just chewing his food. So it would take him like an hour and a half to eat a piece of toast. Like he'd just eat like this, like he just like started getting smaller and smaller and smaller because it like took him all day long just to be able to eat small amounts, and that's because of that low oxygen. So very tired. They may seem very slow moving. And that's O2. O2 levels are low. But what really messes up the pH is carbon dioxide. So CO2 levels, they begin to go up. Because carbon dioxide, they can't get rid of it. More carbon dioxide means more carbonic acid. And that eventually leads to this acidosis. You don't wake up one day and you have emphysema. You get emphysema over decades, okay? Whether because you have lung deficiencies, you have lung damage, you were a smoker, whatever happened, there was chronic damage to the lungs that led to scarring. And so oxygen levels just starts to go down over time. Carbon dioxide levels begin to go up over time. So what's the treatment for this? What happens? Yeah, but you can only give them but so much. So there are things, so there's now like emphysema, actually like inhalers and treatments that actually help and expand the alveoli, that actually act to dilate the bronchi to make air going in a little bit easier, a little less struggling. Yeah, but what do you run problems with that? If you're on steroids, what does that cause? Weight gain. It suppresses your immune system, so it makes it really easy for you to get sick. And so they've already got this issue with they can't breathe. Then they get pneumonia. So then they're in the hospital again because of that. So like that respiratory system, they try to stay away from that. There are some non-steroidal bronchodilators that they use now that have really kind of helped improve lung function. But so treatment, oxygen therapy, some trying to improve diffusion. So my grandfather was a construction worker, he was a logger, he was a smoker his entire life. And he was diagnosed with emphysema when he was in his mid-50s. And like by the time he was in his early 60s, like he didn't remember my grandmother because of low oxygen levels. So he had like dementia all came about. And then eventually he just like suffocated and died. Because that's what happens. So as that lung damage progresses, less and less oxygen gets in, and eventually you can't survive from it. So there's really there's no cure for this one, okay? Because it's because of lung damage. Those are the most common. These are the two that you're going to see more with patients. They're going to have too much acid being made or too much lung damage for them to be able to get good diffusion. Acidosis problems are what usually end up putting people in the hospital. Alkalosis, you're not going to see it a whole lot just because it's a little more rare. Metabolic alkalosis, if you had somebody that ate an entire box of Tums, they might come in with metabolic alkalosis. Because what is Tums? Tums is a antacid, which means it's a base. So metabolic alkalosis, if you overdose on an antacid, you might see that. It's rare for you to make too much base in the body because most of the waste products that you make, they're all acids. And so you just dilute, you just get rid of them through the kidneys, you exhale them, that type of thing. But if you overdose on antacid, and they'll come in and they'll be like really shaky because remember, alkalosis hyperstimulates the nervous system. So they'll seem kind of like sort of shaking, tremors, that type of thing. So in this, you just start large IVs. If it's terrible, you might end up giving them some acid to try and balance that pH. Just have to be really careful about that. Overdose on antacid increases the base levels in the blood. So treatment for this, IV. Dilute it out, get their kidneys to flush that excess antacid out. Figure out why they're actually eating an entire box of Tums. I had a friend that used to drink my Lanta. He had a lot of acid reflux. And so anytime he'd eat, he'd be like, oh, it sucks. So he just would take swigs of it. And I was like, dude, you're going to end up in the hospital one of these days.
A lot of pregnant people, they get a lot of indigestion and stuff like that.
Mm-hmm.
And they eat a lot of Tums as well.
Mm-hmm. So large amounts of them can actually cause the metabolic alkalosis. Respiratory alkalosis is when you're moving air too fast. So when are you doing that? When are you moving air too fast? Because acidosis is when you can't move oxygen, carbon dioxide. No. Hyperventilation. Okay. Usually it's because of the panic attack, the stressors, that type of thing, some emotional distress. And so the person, I always think of the Blair Witch Project, where she's doing all of this rapid breathing. I'm whoo, I'd be boom. Emotional distress increases respirations because if you breathe really fast, what are you getting rid of? You're blowing off all your CO2. And if you're getting rid of lots of CO2, you're getting rid of lots of carbonic acid. And that can cause the equilibrium, cause the balance of the blood pH. Well, and you can try things first. What's one thing you can make somebody do?
Breathe in a paper bag.
Yeah, breathe in a paper bag, okay? And it's really better if you do it every other breath, because if you just do that consistently, you can like shift yourself the opposite direction pretty fast. But worst comes to worst, eventually what will happen? They'll pass out. And guess what? Their brainstem will take over. And they will actually like stop breathing. Don't do like rescue breathing for them. Just watch them. Just sit there and watch them a bit, because eventually carbon dioxide levels will come back up in their blood, and that will tell their brainstem to start breathing again. Because carbon dioxide is actually the trigger for respirations. That's why you breathe when you're asleep. It's the trigger that tells your brain, we need to inhale, CO2 levels are going up. So then you inhale while you're sound asleep. So it's your brainstem that regulates that respiration. So for somebody that's in emotional distress, that hyperventilates, talking them down is really what you're supposed to do. But otherwise, put them in a place so if they do fall, they're not going to hurt themselves. Calm. Rebreathing. Pass out, whatever. Okay? But those are the things, those are just examples of what can cause imbalances. And so you understand metabolic compared to respiratory. Metabolic means you've either ingested too much acid or base, you've gotten rid of too much acid or base, your body's making too much acid or base. Whereas respiratory imbalances is because there's something going on with your lungs. You're not getting good diffusion, or you're doing diffusion way too fast. All right? So they give you their example too, but I just like summarize them. I think they're pretty easy. They're not terrible. Okay? So to go through those, I'll quit there. We're a little early, but I'll quit there. I've had enough for one day. It's hot in here. Okay? So we will pick up with 10 on Monday, right? We do have class on Monday. No. Next week is Thanksgiving. We don't have class on Wednesday. Okay, there's no classes next Wednesday. So we have Monday. So we'll work on chapter 10 on Monday. So I did open the pre-lectures. If you hadn't done 10, I made sure I extended it through next Monday. So if you have any pre-lectures for 10 and 11, you can go ahead and do those. I think I opened 12 too. So you can go ahead and do 10, 11, 12, the pre-lectures, and get them all done.